Microscopic black hole in Paris. Would it swallow the city? Imagine this. A microscopic black hole, smaller than a grain of sand, suddenly appears in the heart of Paris. Your first thought might be instant, city-wide destruction. But the reality, as physics often reveals, is far more complex and, surprisingly, less catastrophic than you might initially imagine. The key to understanding the potential impact lies in the black hole's mass. While it might be incredibly dense, its size being smaller than a grain of sand implies a relatively small mass. We're talking about a mass perhaps comparable to a small asteroid, not a stellar behemoth. Mass is what dictates a black hole's gravitational pull and, consequently, its ability to consume matter. A tiny mass means a tiny gravitational influence, at least initially. So what happens when this minuscule black hole materializes? It will, of course, exert a gravitational force, attracting nearby objects. However, this pull will be surprisingly weak, especially at any significant distance. Earth's own gravity, for example, will be far stronger than the black hole's pull on anything beyond a few meters. Even the Eiffel Tower's gravity, minuscule as it is, would outweigh the black hole's influence on distant objects. Think of it this way. The gravity of a nearby car would likely be stronger than the black hole's pull on something across the street. It's all about relative mass and distance. Now let's consider what happens as the black hole begins to accrete matter, pulling in the atoms and molecules around it. As it consumes this matter, it will grow, albeit slowly. This accretion process is where things get interesting because it releases enormous amounts of energy. Matter spiraling into a black hole heats up to incredible temperatures, emitting powerful radiation. This energy is primarily released in the form of radiation, including X-rays and gamma rays. These are incredibly dangerous and deadly within a certain radius. The rate of accretion is crucial in determining the extent of the damage. If the black hole's mass remains small, its gravitational influence will remain limited. It would likely only consume its immediate surroundings, perhaps a few buildings or a small area. The growth would be slow, atom by atom, molecule by molecule. The city wouldn't be swallowed in minutes or even hours. The process would be far more gradual and potentially self-limiting. Here's another crucial factor. Black holes are not eternal vacuum cleaners. They are subject to something called Hawking radiation. Hawking radiation is a quantum mechanical effect that causes black holes to slowly evaporate. The smaller the black hole, the faster it evaporates. The evaporation rate is inversely proportional to mass. This means our microscopic black hole, with its minuscule mass, would evaporate relatively quickly. In fact, it's entirely possible that the black hole would evaporate before it could consume a significant amount of matter. This evaporation could occur before it even finishes consuming the first building. So, what's the verdict? The sudden appearance of a microscopic black hole in Paris would undoubtedly be a devastating event, but it wouldn't necessarily lead to the complete destruction of the city. The extent of the damage would depend on a complex interplay of factors: the initial mass of the black hole, the rate at which it accretes matter, and the rate at which it evaporates due to Hawking radiation. The immediate area around the black hole would be obliterated, and the radiation emitted would be deadly. However, the complete swallowing of Paris, as dramatic as it sounds, is highly unlikely. This thought experiment highlights the fascinating interplay of gravity, radiation, and the peculiar properties of black holes. It's a terrifying yet captivating glimpse into the extreme physics of our universe.